Homework 5, problem 7. Find the magnetic field at the point P here along the axis of a finite length solenoid. In order to do this one, you could try using the Biot-Savart law, but I actually think it's easier if we just build this from a bunch of loops, which we've already done, right? In problem 6, we found the magnetic field a distance d from the center of a current loop, and so all I have to do is treat my solenoid as a bunch of current loops, and I'm going to say that the width of these current loops is of course dz. So the expression that I'm going to write down in this case is that the total magnetic field is going to be the integral of little microscopic magnetic fields for each infinitesimal width current loop that I'm looking at. But I have I have that dB, that's this expression here for the single loop, right? For the single loop, I found this expression, which is mu naught I over 2. I'm going to put an I prime here. Now let's go ahead and still call the radius of our problem A. So we're going to get A squared over A squared plus Z squared, where Z is going to be the distance below. So this is going to be Z. A squared plus Z squared, 3/2. That's it. Now the I prime I have to think about a little bit. The I prime is actually going to be k times dz, where k is in. So this I prime here, I prime is equal to the k times dz, which is of course going to be in dz, where I is the current running through our solenoid and n is the number of loops, the number of turns per unit length that we're looking at. And so plugging this expression in here for the magnetic field, I get the magnetic field is now mu naught I n over 2, mu naught I n over 2, and then I'm going to have an integral dz from, let's say this is z min to z max, of a squared over a squared plus z squared to the 3/2 power. Now, lazy guy, don't want to evaluate that on my own, so I use Mathematica, and I can then write this down. This is a magnetic field. It is equal to mu naught I n over 2, and then I'm going to get this expression. I would get this z max over a squared plus z max squared to the 1/2 minus z min over a squared plus z min squared to the 1/2 power. Okay, but now I can do a little bit of trig. Now if I look at this problem, this distance here is z max, and this distance here, okay, is this square root of a squared plus z max squared. And so z max over that is actually the opposite over the hypotenuse, and so that's the sine. Sine? Nope, that's not z max, that's not a over this. This is adjacent over the hypotenuse, is the cosine. Good, should have been the cosine. And so writing this in terms of these angles, I find that this b is equal to mu naught I n over 2 times cosine of theta 2 minus cosine of theta 1. And the interesting thing here is, if we look at this for the case of an infinite solenoid, then theta 2 is going to be 0, and theta 1 is going to be pi, because it reaches around all the way to the other side. and cosine of 0 is 1, cosine of pi is -1, so I'm going to get 2 out of this. And so for infinite solenoid, for infinite solenoid, I find that the magnetic field is going, for infinite solenoid, I guess first I get that theta 2 equals 0 and theta 1 is equal to pi, and that's going to give that the magnetic field, right, is mu naught I n, which is exactly what we want to find if we, because that's what we would find for an infinite solenoid using Ampere's law.